Okay, hello everyone. I'm a gamma ray astronomer from Heidelberg, and I want to talk about the Astropy project. So what is Astropy? It kind of all started on the Astropy mailing list on June 9, 2011. So there was this guy sending an announcement. We would like to let you know that our recent release of the hopefully useful contribution to Python's astronomy community, a PyAstronomy package. And then he goes on to describe what it does. And the immediate reply was to change the topic to proliferating PyAstrolibs. And hopefully, without sounding too critical, I'm going to ask, do we as a community really need yet another separate Python library for astronomy? And this kind of triggered the creation of the Astropy project. So, I mean, Python has been big in astronomy for a decade at least, and there was this Astropy mailing list, but there was no core Astropy package, and the problem really was that efforts were scattered a lot. Many astronomy packages that re-implemented functionalities had different APIs, and this was bad for the astronomy Python community as a whole. And the solution to this problem kind of is just to start the Astropy project, which is a community effort to develop a core package for astronomy in Python and to foster interoperability between Python astronomy packages. So there's these three project coordinators: Perry Greenfeld from Space Telescope Science Institute, Thomas Robitaille from MBA for Astronomy, and Eric Tollerud from Yale. And the Astropy project kind of consists of two components, which is the Astropy core package, which contains the stuff that's useful for most astronomers. And then there's the Astropy affiliated packages for more specialized astronomy applications. And they can leverage the Astropy infrastructure, packaging, testing, documentation by using a package template. So now it's kind of 3 years later, and I would say this has worked out really well. Astropy has been showcased on GitHub recently as a science showcase, saying that 3 years after the first commit, more than 75 researchers have contributed over 1,600 pull requests. And here you can see the commit activity on GitHub over the last 3 years. There's also institutional support from Space Telescope Science Institute. They have gotten funding to develop generic data analysis tools for Python to support this upcoming space telescope. The data analysis leads, and most of their effort will go to Astropy and affiliated packages. So now let me talk a little bit about the core package. And since most of you are not astronomers, I will focus on one sub-package that is probably most useful to scientists in general, which is astropy.units. But first, an overview of the Astropy core project. There have been 3 major releases. The first one in February 2013. The latest stable release is 0.4.1 from August this year. The Astropy 0.2 paper was published in Astronomy and Astrophysics, which I think is a nice sign that an astronomy science journal accepts a paper that only presents a software without a science application. I also wanted to mention that Astropy has started this process of having APEs, Astropy proposal enhancements, for significant changes to the Astropy core, which is similar to the Python PAPs. And they have already been used for things like the configuration system and the setup system and coordinates and a few other things. The Astropy had 2 Google Summer of Code students in 2013 and 6 this year. This has been a big success, and it's close to 10,000 commits from 90 contributors at the moment. What is the core functionality? I'm not going to read off this list. As I said, I will concentrate on units, quantities, and constants on the following slides and show some code how you can use this. I also wanted to mention that there's a high-level time class. So if you need very high precision time, this is made up out of two floats. And it has very accurate timescale transformations. Astropy has a high-level table class. And the difference to the pandas data frame is that it allows for array columns and metadata and masks. So, I mean, I think they were thinking about using pandas data frames in Astropy, but then they decided to go their own way and create a table class. And there's a modeling fitting framework that uses SciPy Optimize, which might also be of interest for other scientists. But now going on to showing a little bit of codes with units and quantities. So there's the Astropy units package, and you might ask yourself why, because there are many Python units and quantity packages, but actually none of them fit all the requirements for units in Astropy. So we needed separation and conversion between systems like SI and CGS. We needed equivalencies, for example, between frequency and wavelengths, and multiple serialization formats, some of them specific to astronomy, like FITS and VO unit, where VO is the virtual observatory. So what happened was that the PyEnbody units code was taken as a starting point and then developed over the past year or two into Astropy units. And the following slides give you a short introduction to some of the basic features. There's much more to it, and I'm not an expert, just I would say a user and fan of Astropy units. So if you have any tricky questions, I'll try to answer them, but I might not be able to. Here's some code. So the Astropy units package provides a unit and a quantity class, and then you can create units by like this, or a quantity like this. The Astropy units namespace also contains a lot of unit objects, and you can use arithmetic to create units and quantities. So you have these 2,600 things in the units namespace, and you can say u.meter with tab completion, and you get the meter unit, and then you can say 42 times u.meter, and you get a quantity object which represents 42 meters, and you can do more arithmetic to construct all kinds of quantities. Quantity is a Numpy array subclass, so you can make quantities that represent arrays of values with the same units, again by multiplying a list or a Numpy array with a unit. Quantities have useful attributes. For example, .value gives you the value, .unit the unit, and then you have a description. You can get the physical type, and you can find equivalent units. For example, the electron volt is equivalent to joule or erg. One thing you often want to do is convert quantities to a different set of units. So if you have 42 kilometers per hour and you want to know how many meters per second this is, you can just use the to method. There's also the decompose method, which you have to use. For example, if you have a speed and then a distance, and then your distance divided by speed, you get something like 0.02 kilometers second per meter. And that's not very useful, so you have to call .decompose it, and then it will produce irreducible units, and it'll tell you it's 22 seconds. If you like SI units, you can just ask what is the value of what is this quantity in the SI system, or you can ask what is this quantity in the CGS system. Kind of not everything is put into the normal units namespace. Weird units like the imperial units are not in there by default, but you can get at them, of course. So if you want to know what 42 kilometers per hour is in miles per hour, you can do it this way, or you can do it this way. And the Astropy constants also provide the constants as quantities, so you can quickly compute the rest energy of the electron in MeV if you need that, if you're a physicist. So a few comments about quantity and NumPy. As I said, quantity is a NumPy array subclass, and it plays nicely with most NumPy functions. For example, you can ask what is the sine of 90 degrees, and it's okay, and you can ask what is the cosine of 90 degrees, and it's almost 0, so that's okay. Or the mean and the standard deviation work. And just one more comment. I mean, using quantities in your analysis script is very useful because, for example, if you ask what is the cosine of 90 meter, you get a type error. But there's some issues when you use quantity with NumPy and SciPy functions. For example, there are functions that silently drop the units. So if you have a quantity and you call NumPy array on it, it drops the units. Or if you call NumPy.dot or NumPy.cov on it, it drops the units. And there's a few functions that don't reinitialize the unit property, like hstack. You get out this quantity object where the units are not initialized. So if you're a NumPy developer and like Astropy units, then please look at this issue and help resolve some of these issues. So this is just a last slide with code showing a few application examples of quantities in Astropy. So units have been incorporated into some parts of Astropy already. For example, the Astropy coordinates package. So this just shows that you can construct a sky coordinate and then online look up from a name where this object is in the sky. And then if you look at the right ascension and declination of this object, you'll find that they are quantity subclasses. So another package where quantities are used already is Astropy cosmology. So you can ask what's the age of the universe according to this Planck 13 model, and you'll see that it's 13.7 gigayears. There's other parts of Astropy where quantities have not been integrated yet, so there's quite a bit of work left for the Astropy core and affiliated packages to do this in the coming months and years. Now I want to talk a little bit about Astropy affiliated packages. These can be either functionality that is very heavily under development for the core, so it's easier to have a separate repository for a while, or it's more specialized functionality, or it can be used for packages which don't have a BSD license. And the idea is that any astronomy package can apply to become an Astropy affiliated package, but it should adhere to some Astropy coding testing and the docs guidelines. One thing I really like about Astropy is that for the core package and any affiliated package, you can just say Python setup.py test, and it'll run the tests, and if you say -- help, it'll show you all the options, how you can select tests and what you can do about them, and the same for building the documentation. This is something that's different for a lot of Python packages, and would be nice to have a standard and have something like this work for all Python packages, I think. So here's a list of existing affiliated packages. I'm not going to go through it again. I'm just going to highlight 3 of them: GammaPy, phototils, and WCS axes. But there's many, many more, and more coming, I think, in the coming years. So what is WCS axes? I just chose this as an example of an affiliated package that will be included in the Astropy core soon, because this is useful for most astronomers. So WCS axis is a framework for making plots of astronomical data in Matplotlib, like the one shown here. And WCS means world coordinate systems, so it means how pixel coordinates map to sky coordinates via projections. And you can see that what it does is it plots coordinates, for example, in galactic longitude and latitude, or equatorial right ascension and declination. And what you can see is that there's also grid lines denoting these coordinates. So this really provides mainly one class, the WCS axis class, which is a subclass of Matplotlib axes, but it knows about Astropy coordinates and quantities and world coordinate systems. There's phototils, which I just chose as an example of an Astropy affiliated package that might be included in the Astropy core, because it's useful for a large fraction of astronomers. What it does is source detection and characterization of astronomical images. At the moment, there's aperture and PSF photometry implemented, heavily using SciPy ND-image and scikit image. And here's just an example that you could use. You could run the DAO find algorithm on some image with some parameters, get back a table of sources, and then create apertures around these positions, which are illustrated by the red circles here, and then measure the flux within these apertures in the image. GammaPy is a package I started for gamma ray astronomy, and it's just an example of an affiliated package that will never be included in the Astropy core, because it's useful only to like a sub-community of astronomers. And what it does is it provides tools to simulate and analyze astronomical gamma ray data from ground and space-based telescopes, as illustrated here. And we had an 0.1 release a few days ago, and I'm hoping that a small community of Python enthusiasts will start using and contributing to it. One more thing, I wanted to mention ASV, A-speed velocity. This is not an Astropy affiliated package, but it's a tool for benchmarking Python packages over the lifetime. You can find it here, and you can check the Astropy benchmarks as an example, what it does. So this is not really Astropy specific. Anyone can use it for to measure the performance of the Python package over time. It's really easy to set up. You run a quick start and answer a few questions about your project, and then you tell it to run the benchmarks. No, then you have to write a few benchmarks, which are just Python scripts, and they pretty much use the same method that's used for unit tests these days, where you have a standard naming convention for tests, and test runners will find it. So here you have the naming convention that if you have a function called that starts with time, it's something that should be benchmarked, that the time should be measured, and if it starts with mem, it's something that where the memory usage should be benchmarked. And if you need some setup, then you can create a class with a setup function and time methods. And once you've written a few benchmarks, you can then run them for whatever commits you like. And this might take a long time. It'll create a virtual env and install your package and all the requirements for each commit, and then run the benchmarks. And then you can create quickly an HTML report and look at it in the browser, and what you'll get is something like this. That's just the result of one given Astropy benchmark, and then you can click on commits and see how they change the performance of this benchmark. So this is really useful and a nice tool, and you might want to check it out for your project if you don't have performance benchmarking set up already. So just to finish up, the next steps for Astropy, there's lots of improvements in addition to the core package to be done. Finish modeling and coordinates, add generalized world coordinate systems, image utilities, spherical geometry routines, use quantities throughout Astropy. The Astropy 1.0 release is scheduled for December this year, and we've settled on a 6-month release cycle with 2-year long-term support. The other thing that's going to happen is that the ecosystem of Astropy affiliated packages is going to extend, and I really like this, that this might lead to a future of open and reproducible science in astronomy by more people sharing their code and making the analyses reproducible. I also wanted to mention that there's an upcoming Python astronomy workshop spring of next year at the Lawrence Center in Leiden, and you can find some information here. Thank you for your attention.
Time for a few questions.
Hi there, thanks. That was good. Just about the units package, you're quite right, it has very broad interest, I think. I'm just wondering, why isn't that a separate project? Why do you keep that as an internal package? Wouldn't it just be better to split it off at this point?
I think there are like 10 to, I don't know, 50 different unit packages on PyPI. And I mean, I wasn't involved in these decisions, but I think it was Perry Greenfield and Michael Dredboom from Space Telescope Science Institute that, where is this? That looked at all of them or most of them and had certain requirements for Astropy, and apparently none of them worked, and PyEnbody was the closest one, and then they just kind of went with this and developed it extensively further into Astropy units. But I agree, it's something that it would have been nice if this would have been solved at the SciPy level or something like that.
Any other questions? I have one more question about the benchmarking. It looks, from the description you gave, very similar to vBench. Can you point out some of the differences? Why would you use this over vBench?
I don't know this other tool.
Okay. I think it's written by...
The docs are pretty good. You might maybe just have a look, or I can look at the other tool afterwards.
Thanks. Right. Thank you, Christoph, and time for lunch.